TTP-Based Hunting, a methodology overview. In this module, we will give an overview of the process by which you can hunt for adversarial activity based on knowledge of their tactics, techniques, and procedures, or TTPs. In this module, we'll provide an overview of the methodology, the objectives for this curriculum, and prerequisites that you'll need. We'll provide a background over approaches to measurement and review some of the legacy approaches to detection. Then we'll review the principles underlying TTP-based hunting, including David Bianco's Pyramid of Pain, an introduction to the ATT&CK Framework, which is the way that Mitre has decided to describe and categorize adversary TTPs, and then go through an overview of the 7-step hunt methodology. To start, let's give an overview of the methodology. This is going to be our map throughout these modules for the 7-step process and where we are in that process and how the step you're on relates to the other steps in the process. This V diagram is the navigational map that we'll continue to come back to orient you throughout this training. So let's walk through it. There are 7 steps here. The first step is to understand adversarial activity, and you create a model to do that. Mitre uses the ATT&CK Framework for this. Based on that knowledge, we move into a second step, which is to develop hypotheses and abstract analytics. These are usually written in English or pseudocode, and they try to capture the essence of the behavioral invariant activity that is associated with those malicious TTPs. The third step is to determine what data we'll need to observe that activity and test our hypotheses. Once we know the network or system on which we need to hunt, we can filter down all of that abstract information to only what's relevant for that particular hunt. Once we have that repository filtered down appropriately, we can go on to the operational network, identify any data collection gaps that we have relative to what we've determined we need, and try to mitigate those. Then, once we've got adequate data collection, we can start implementing and testing our analytics. Finally, once we've validated our analytic approach, that it will detect adversarial behavior when it is present and it won't have too many false alarms, we're ready to operationalize those analytics and conduct our hunt. This module is the first of several. There will be one module for each of the steps in this methodology, and at the end of the full curriculum, you should have a decent understanding of this methodology and be able to go execute it in your operational environment. In this particular module, we'll be giving an overview of the methodology and some background information. And by the end, you should be able to define the 7 steps of the methodology and contrast the key elements of this style of hunting based on TTPs with other styles of hunting based on profiles, signatures, or anomalies. In this course, we will be referencing lots of examples in Windows, and so a good understanding of Windows will be helpful as you go through this material. In addition, some familiarity with a SIEM like Splunk or Elk will help you follow along with the later stages of this process when we start talking about implementing analytics. It'll also be useful to have a background in networking fundamentals and an ATT&CK before you begin this course. And in order to follow along with our examples and exercises, it'll be useful for you to have an environment in which you can deploy some sensing, data collection, push that into an analytic environment, and experiment with your own analysis. As background to this approach, let's talk about a few key ideas when we talk about detection generally, and go over some of the legacy approaches to detecting malicious activity. There are many ways to think about the accuracy of a particular analytic. You can think about false positives, false negatives, true positives, true negatives. There are words in use in this domain like accuracy, precision, and recall, sensitivity, and specificity. In this series, we're going to use the phrases recall and precision. Recall will mean that if the event occurs, our analytic will fire. Perfect recall will mean we catch every instance of the thing that we're looking for. Precision means that you're not catching things that you don't intend to catch. So a perfect precision would mean that you're not getting any false positives. Obviously, ideally, we'd like to have perfect recall and perfect precision, which would mean that every time an alert fires, it is definitely something malicious and interesting and something that we want to investigate. There will be no false positives, but we also won't miss anything that we should be finding. However, in reality, there's often a tension between these two things, because in order to get better recall, we need to sort of open up the aperture on our analytic and include more things so that we include more of the malicious things that we're really looking for. However, in many of the ways that we can do that also end up including more false positives because we're broadening that analytic. On the flip side, if we try to get better precision, then we end up tightening up the analytic scope and excluding more things so that we have fewer false positives. However, many of the approaches to do that also exclude some of the true positives because that scope has been narrowed. And this is a theme that we'll see recurring throughout this process. Now that we have an orientation on precision and recall and the tension between the two, let's have a brief overview of some of the other approaches to hunting, which are complementary to TTP-based hunting, but distinct. One way to think about the different approaches is in how they define bad or malicious activity. One approach is often referred to as signature-based. In this approach, we try to explicitly define what we're looking for, or what's malicious, as a very specific pattern. This might be a string that you're looking for in a file, or a specific IP address or domain name. Another approach is to deny everything except for specific things that are defined as allowed. And a third approach is to run some kind of statistical analysis over the collected data. That might be network traffic, it might be a list of IP addresses, it might be a list of binaries, it might be certain user activity, and look for anything that is statistically deviating from normal. And in this approach, we're then going to make the implicit assumption that anything that is anomalous is also worth investigating because it's probably malicious. A second aspect of these different approaches is where they're looking for malicious activity. One common place to look for malicious activity is at the network perimeter. Another example location would be on hosts inside the network. So one of these approaches is signature-based detection. In this approach, we reverse engineer known malicious things, whether that's binaries or the domains of command and control servers, and we try to find signatures that characterize those malicious things, but do not also characterize benign things. And these are often expressed in the form of so-called regular expressions, or regexes. And these are essentially string pattern matchers, where we can use wildcards and other functions to match in a more fuzzy way than an exact string match. So examples of doing this would be to use specific hashes or specific file names, patterns in data, specific port numbers, IP addresses, domain names, and sometimes many of those signatures can be combined into a composite signature. And there are lots of commercial products that fit into this category. And this approach has some advantages. It can have pretty good precision. If you're measuring a very specific string, then you're unlikely to get something that doesn't have that specific string. And it's fairly easy to implement these things because there are lots of products out there that will do regular expression matching. And so once you express your signature in that way, you can use those products to scan through files that are being attached to emails or network traffic. However, in practice, this often ends up with worse accuracy than we'd like. For one, it can be very difficult to write a signature that captures all of the things that you're looking for and nothing else. Often these strings are common to other benign files or network activity. Another downside is that this approach often requires the accumulation and storage and use of an ever-growing list of signatures that need to be blocked. There's a lifecycle management required for these signatures to make sure that they're still up to date, and in the end, these tend to be relatively easy things for adversaries to evade. In modern attacks by APTs, but also in open source red teaming tools, changing these signatures is as easy as setting a particular configuration or flipping a switch so that every usage of the tool on a different target machine can have a different set of hashes. Each campaign can have a different set of domain names associated with C2. And so this is a pretty ephemeral thing to look for to describe malicious activity. The second approach is, instead of trying to create these strings or patterns that match all of the known malicious activity, would be to define what is allowed and then block anything else. So instead of trying to define what's bad, we define what's good. And you might think of this as a profile-based detection approach. Now, this approach has a different set of pros and cons, as you might imagine, from signature-based detection. On the pro side is that this is a very restrictive environment for an adversary to operate in if this is strictly enforced. So in an environment where you could really reduce the number of allowed applications and network connections to a very small number of things, you've also constrained the adversary to operate within that same small scope. However, in practice, many exceptions end up needing to be made because legitimate users need new applications, existing applications need to be updated, content is being created, new websites are being viewed, etc. And so this becomes a configuration management problem for the security team to keep this list of allowed activities and binaries up to date. It can become very restrictive for the users as they try to do their job and are running into the same barriers that you've imposed for the adversary. And so in practice, this can be a difficult thing to implement in a way that is that accommodates the benign uses of your legitimate users, but truly restricts the adversary. A third common approach is anomaly-based detection. In this approach, the analyst often does a statistical-based analysis. Sometimes it's based on math, sometimes it's based on machine learning, sometimes it's just based on the heuristic analysis of the human analyst. But the gist of all of these approaches is to try to establish a baseline of what's normal and then look for deviations from that baseline. In this approach, there's an often implicit assumption that whatever is normal, whatever is in the baseline, is benign and should be allowed, and whatever is deviating from that baseline is at least worth investigating, if not malicious. On the upside, this approach does have the potential to detect previously unknown attacks. With the signature-based example, that's really oriented toward detecting known bad things, whereas in this approach, it's a little bit more open-ended, and if something malicious happens that is anomalous, but you didn't see before, this does at least have a chance of detecting it. However, similar to the profile-based detection, in practice, this is a more difficult thing to implement successfully for a few reasons. One is that the baseline of a typical network doesn't tend to be stable. Patterns change, what is normal changes as users do different things. Different users have different roles. On different days of the week, they might do different things. And so the envelope that you have to create around defining that baseline can be pretty large and highly variable over time and between users. A second downside of this approach is that it tends to require a higher skill level for the analyst. Either they need to be very well steeped in what's normal on that network and have a pretty large working memory of what they should expect to see on the network, or it might require some advanced statistical analyses or machine learning skills to implement this in a more automated way. Another problem with this approach is that malicious actors understand that defensive systems try this approach, and they will try to blend in with what's normal, and that helps them evade detection, especially in the typical situation where the envelope of what is considered normal and benign has to be so large due to the variation in what's normal that we talked about. And as a result of all those factors, what ends up happening is that what's normal, what's statistically normal, or what you've captured in your baseline might very well include malicious activity, and what's abnormal will often include benign activity. And part of the issue here is that the overall proportion of activity on a network that is malicious is typically fairly small. And so this ends up with a very high false alarm rate in practice many times, because the majority of the anomalous activity turns out to be benign. And so analysts spend a lot of time chasing down leads based on anomaly detection that end up not resulting in a true detection. So with that background, let's now talk about TTP-based hunting. Now keep in mind that this approach will incorporate some of the aspects of those other legacy approaches. There'll be a little bit of anomaly detection involved here. There'll be a sense of writing signatures and defining what's malicious and what is benign. And this approach can be complementary to those other approaches. But it is distinct, and this course is designed to help us understand this approach and be able to implement it in partnership with those other approaches. So let's talk about the two dimensions for TTP-based hunting that we had talked about for the other approaches. Where are we sensing, and how are we defining bad? So first off, where to sense. A lot of the legacy approaches have focused on the network perimeter, and they focus on network traffic at the perimeter to keep the malicious activity out or detect a massive exfil at the end of the adversary's campaign. Of course, antivirus approaches have focused on the endpoints. Both of those tend to use a more signature-based approach. TTP-based hunting, as we'll see, will start with a definition of what adversaries have to do from a behavioral perspective at the TTP level of abstraction, and from that understanding derive what kind of data we need to collect to support our hypotheses. And what we will find out is that that approach is going to need data much more often from inside the enterprise, including on the hosts. The second dimension that we talked about with the other approaches is how to define malicious. In one sense, it was about regular expressions and the strings that we're looking for. With anomaly detection, it was what was statistically normal was good, and what was statistically abnormal was assumed to be bad. However, as we saw, neither one of those really captures the essence of malicious activity. So we need a better way to describe those behaviors. So let's look at the three main approaches and how they define behaviors. In summary, we can define what's allowed and block everything else. We can define what's malicious and allow anything else. Or we can develop a baseline and look for anomalies. So we looked at one way of defining what's malicious, which was around the signature-based approach. And we saw some of the downsides of that. So what if we took that same kind of approach, but changed how we're defining malicious to be about behaviors and TTPs rather than the lower level indications of compromise like hashes of binaries or IP addresses? And why should we look at malicious activity from the perspective of TTPs rather than those lower level indications of compromise or IOCs? Well, for one, in order to have an IOC at the level of an IP address or the hash of a binary and know that that is related to something malicious, by definition, something malicious has already occurred. Someone has had to detect that through presumably some other means of detection. They would have had to have done the reverse engineering or analysis and figured out what the signature should be associated with that, publish it, and then have other organizations adopt that and use it. And therefore, this is a pretty reactive approach and tends not to help the initial victims unless you have some sort of advanced knowledge before even the first attack is launched. And as we talked about earlier, these tend to be things that are pretty easy for an adversary to change. We're going to talk about that a little bit more with David Bianco's Pyramid of Pain. On the flip side, TTPs are really more constrained by the technology on which the adversary is operating. For example, if they're going to conduct their operation on Windows, they're going to need to interact with Windows. And they're going to interact with Windows in using the APIs that Windows presents in a lot of cases. And so there's a natural constraint there for adversaries at the TTP or behavioral level that we can capitalize on as a defender to give us a bit of an advantage. Now, David Bianco captured this in 2013 in his Pyramid of Pain. And in this pyramid, he lists some of the different ways that you can characterize malicious observables, such as hash values or domain names. And he put them in order of how difficult they are for the adversary to change. So let's walk through these different layers. At the bottom of the pyramid are hashes. For those who don't know, a hash is just a number that results from applying a function to an input, such as a binary. You input a file to this function, and out pops a number. The number is created using a cryptographic function that is designed to come up with a completely different answer if even a single bit of the input has changed. And the original design of this was to validate that the contents of the file that you're looking at are exactly the same as what you would expect, with a concise representation of that file being the hash. Unfortunately, using that same process and that same hash value to look for malicious files makes it pretty easy for the adversary to evade you, because in the design it was ensured that even a change of a single byte would result in a different hash value. Therefore, the adversary just needs to change a single byte or bit, and their hash changes, and they evade your detection. The second lowest layer of the pyramid of pain is IP addresses. IP addresses are just numbers that are used to route IP traffic through a network, and they are dynamically assigned, and they get reassigned regularly through things like DHCP. They could be masked behind a network address translator or proxy. And so these are fairly unreliable indicators, and again can be easily changed by the adversary. The third lowest layer of the pyramid of pain is domain names. These are strings like www.google.com that are the sort of human-readable version of the IP address. They're registered with the domain name registrar, and they map back to the actual IP address of the server. These take a little more effort to change because you have to modify the domain name system and register a new domain name, but this is still a very trivial thing for an adversary to modify. As we move into the top half of the pyramid, we get to the level of network and host artifacts. So these are things like the files that are saved to disk during a malware operation, or the names of registry keys that are used by malware, typos in the code, or in headers of network traffic. To change these, the adversary needs to have a deeper understanding of what they're doing in order to make the modification that would change these artifacts without changing the fundamental capabilities of their malware. So this is a bit harder for the adversary to change, and therefore the asymmetry starts to shift a little bit more away from the adversary and toward the defender if you're looking for these artifacts. Near the top of the pyramid of pain is the level of tools. In order to change what tool an adversary is using, they will probably either need to develop their own, which will require a decent amount of skill, or they will need to conduct new training in order to understand how to use the new tool. And those things are much more expensive for the adversary to modify than the lower levels of the pyramid of pain. So looking for tools is a more robust approach than looking for hash values or IP addresses. At the top of the pyramid of pain is the level of tactics, techniques, and procedures. These, as we had discussed before, are going to be limited. They're constraining to the adversary because they're limited by the functionality of the target technology. The tactics are really intermediate level objectives that adversaries need to accomplish regardless of their overall aim or skill level or the particular tools or infrastructure that they're using, and they rarely change. Even at the technique level, which are ways to accomplish those tactics, it's a fairly small number of techniques that are being used for a given tactic, and they don't tend to change much over time. Because of these difficulties for the adversary to make modifications at this level, there is an advantage to the defender if we can detect these TTPs, because if we can detect those TTPs, that's a tractable number of things to handle for the defender, and it's very difficult for the adversary to do something that isn't using one of these TTPs. So if we're able to mitigate or detect them, then we're going to have much better coverage over the kinds of things that our adversaries can do. So to summarize across these different approaches, in signature-based detection, we need to have a lot of detailed information about prior malicious activity. It takes analysis to figure out what those signatures should be and make sure that they are distinct from benign activity or files, and they're relatively easy for the adversary to change. On the other end of the spectrum, we have anomaly-based detection, which doesn't require much knowledge about what malicious activity looks like. It's much more based on the assumption that whatever is statistically normal is also benign, and whatever is statistically abnormal is malicious. It's a fairly flexible approach and can help you detect things that have never been seen before, but tends to result in a lot of false alarms. In the middle of this spectrum is TTP-based hunting. It does require an understanding of what malicious activity looks like, but it focuses on what it looks like at the TTP behavioral level rather than at the very lowest levels of the bits and bytes of files and network traffic. And it tends to be robust to changes by the adversary because they're constrained at this level of abstraction based on how the target technology works. And remember that these approaches are complementary. We're not saying that signature-based approaches or anomaly-based approaches don't have value. They do. And these can all three work together to provide a more holistic approach to defense. What we tend to find is that in many shops, there's already a good approach being taken for signature-based detection and anomaly-based detection, and the gap tends to be in TTP-based detection, and that's what this course is really about. A key aspect of TTP-based hunting is obviously an understanding of malicious actors' TTPs, and the way Mitre has gone about capturing, describing, sharing those TTPs is through our ATT&CK Framework. The ATT&CK Framework documents and categorizes adversarial behavior at the TTP level in a matrix structure. The tactics that adversaries employ are represented as columns, and the techniques that adversaries use to accomplish those tactics are cells within those columns. The most recent version of ATT&CK also includes the concept of sub-techniques, which are more specific implementations of the techniques. And for each technique or sub-technique, there's a description page that outlines how this has been used, which actors have used the technique or sub-technique, and any mitigation or detection ideas around that technique or sub-technique, along with data collection requirements and the technologies on which that technique is applicable. Adversaries are conducting campaigns in order to accomplish certain effects. And we can think about those campaigns in the terms of a kill chain or a life cycle. There are pre-compromise activities that an adversary has to go through. There are activities that an adversary needs to do between an initial compromise and their ability to create the effect or accomplish their goal that they're after. And then there are a set of effects that an adversary might want to employ. And while Lockheed Martin had created a cyber kill chain model that described adversarial activity sort of at the tactic level, ATT&CK really fleshes that out and gets down into the technique and sub-technique and procedural level to give the defenders much more detail so that they can create mitigations and detections around those techniques. although originally developed with a focus around a Windows Enterprise technology stack, ATT&CK has continued to evolve and expand and now includes pre-attack, which are left of exploit behaviors. There's an attack for Linux, Mac, cloud, mobile, and ICS. ATT&CK captures pretty comprehensively what's currently openly reported in the open literature, but it's a constantly evolving activity and repository of information. So expect that new details will be added, new reporting will be added, new detection and mitigation ideas will be added. It will expand to include more technology spaces as new reporting comes out, and periodically new sub-techniques, techniques, and occasionally even tactics might be added to the framework. As we talked about before with TTP-based hunting, we're really trying to focus on understanding and describing adversary activity at the TTP or behavioral level. And ATT&CK does a terrific job of documenting what we know about actual adversary activity at that level of abstraction. It's an open source resource. It's not the only way to think about adversary behaviors or malicious behaviors, but it's a great resource to get started, and it's what this TTP-based hunting methodology training will be focusing on as our starting point. So with all that background and context, let's dive in to the actual TTP hunt methodology, the 7-step process. We're going to go through the V step by step. We're going to expand on each one a little bit, and this is going to provide you the context so that as you go through each step's module, you'll have a sense for where you are in the bigger process, what kind of inputs you should be expecting from previous steps in the process, how the step that you're in contributes to the overall process, and give you that context and situational awareness. So hunting in general is based on a hypothesis, which is that there are malicious actors out there who want to do something through cyberspace to me, my enterprise. They might want to steal my intellectual property. They might want to deceive me. They might want to create a cyber effect on my mission or business. And they're going to do this through cyberspace. And the crucial thing about TTP-based hunting is that they will exhibit behaviors that are common among malicious cyber actors. And this is where the pyramid of pain concepts are really going to pay off. It's not a valid hypothesis to think that in every instance a malicious actor is going to reuse the same observables at the lower levels of that pyramid of pain. They're not necessarily going to have the same hash values, IP addresses, or domain names. They might not even create the same artifacts on your systems. They might not use the same tools. But what evidence has shown is that there are only a small number of behaviors at the TTP level that an actor can exhibit. And so we can use that to our advantage and focus on those in our hunt. So let's break down this process. As we saw at the beginning of this briefing, the process can be visualized as a V. So let's break that down into its constituent parts. The V consists of different layers. The top layer represents the malicious activity that you are looking for, that the adversary is going to exhibit in your systems. So on the left side of the V, we need to understand what that malicious activity is and what it will look like. We need to document that, and we need to understand that. On the right side of the V is sort of the end of the whole process, and we see that, again, we're looking at the malicious activity level, the behavioral level, and after we've gone through this process, now that we're at the last step of this V, we are detecting that malicious behavior. We can drill down now to the second layer of the V, and this is the analytic layer. These are the analytics that are derived from hypotheses that we develop about the malicious activity model. And once we have figured out what data we need to feed those analytics and collect that data, we will be able to implement those analytics as concrete analytics. We'll take them from an English language hypothesis into a specific query syntax looking at specific data sources. And we'll test those analytics with red team, threat emulation, purple teaming activities, and we'll be able to then use those in our hunt to detect the malicious activity that we started with in step 1. The third layer of the V is the data layer. Based on our understanding of the malicious activity, the malicious behaviors, we've developed these hypotheses and developed abstract analytics around them. But we'll need data collected to feed those analytics. So on the left side of the V, we need to determine what data is required or is preferred to feed those analytics. And on the right side of the V, we're going to go implement those data collection requirements. We're going to try to instrument our systems in such a way that we get the input data we need to feed the analytics that we've developed so that we can detect that malicious behavior. The bottom layer of the V is just a filtering, pivoting step. Essentially, we can go down the left side of the V in a fairly abstract way. We might not even have a particular network in mind to do those first 3 steps of the V. But in order to pivot into the implementation side on the right side of the V, we're going to want to filter down all of those abstract ideas to focus on the time, terrain, and behavior that are applicable to the network in which we're going to be hunting. So another way to break down this V, instead of by layer, would be left and right. On the left side of the V, it's all about characterization. It's abstract. It's going to be English. It's going to be requirements, derivation, and documentation. This is going to be a research-oriented phase. And then the right side of the V is going to be much more focused on execution and implementation. This is where we take the abstract ideas that were developed on the left side of the V, and those could be developed by us or by other people in the community, and we're going to refine those and implement them and validate them in our own network. And we're going to take these abstract ideas and we're going to tune them based on what our particular network looks like. So looking at the overall V, we can see there are 7 steps to this, 3 steps coming down the V on the left as we define malicious activity, we develop our hypotheses, and determine our data collection requirements. There's a 4th pivoting step from abstract requirement generation into the implementation phase. And then there are 3 steps moving back up from data to analytics to malicious behavior as we implement these ideas and end up with detection of the malicious activity that we started out looking for. So let's dive into each of these 7 steps in a little more detail. So step 1, the malicious activity model. We talked about attack. We've got a matrix where the columns represent tactics, the cells are techniques, and in the latest version, some of those techniques then have sub-techniques associated with them that are more specific and detailed. And there are descriptions of what the behavior looks like for those techniques or sub-techniques, how actors have used them, what tools implement them, and some of the recommended mitigations and detection ideas around those techniques and sub-techniques. This is a great starting point for TTP-based hunting. There's a large community that over many years has accumulated real evidence based on open reporting of what actual adversaries are doing to develop this pretty comprehensive repository of information about the behaviors of malicious actors. As we go to the second step of the methodology, we're going to be developing hypotheses and abstract analytics based on those hypotheses. We're going to have a training module about this step, and we're going to dive into this a little bit more. And one of the examples that we're going to take throughout this entire methodology is the technique of scheduled task or job. This is a technique that adversaries could use for several different tactics and purposes, but we're going to look at why an adversary would use this technique, what are the behaviors associated with that technique that are intrinsic to the TTP and not something that is easily changed by the adversary. And we're going to focus on those behavioral invariants to develop a hypothesis. And the hypothesis will be in the form of, if I see those behavioral invariants, it is evidence of an adversary trying to accomplish that particular tactic. Once we have that high-level hypothesis, we're going to decompose it. We're going to break it down and refine it. And some of the things we're going to need to think about are, what are the things that make a malicious employment of this technique look different from a benign use of the same technique? There might be things intrinsic to the way that the technique is employed that we could use for this, and there might be contextual things, preceding events or subsequent events that could raise our confidence that this particular behavior is being used in a malicious way versus a benign employment. Once we've got our hypothesis set, we move into step 3. Now, in this V diagram, this looks like a very sequential process, but in practice, there'll be lots of iterative loops going back to earlier steps and refinements as we go. But generally, we want to define our hypothesis first, and then we're going to come and think through, what data will I need to test that hypothesis? And we're going to talk about 3 primary dimensions to consider for this step, and for most of these steps, which are time, terrain, and behavior. In terms of time, what this means is that you need to collect data while the data exists that provides evidence of this behavior. It sounds pretty obvious, but there are a lot of attempts to hunt that don't take this into account, and they begin collection after it's too late, after the activity has completed and after the artifacts of that activity might be gone. And so we need to keep that in mind right now at the beginning stages of this process. A second dimension is terrain. We need to make sure that we are collecting on the systems and in the networks where the activity will be visible. Again, sounds pretty obvious, but a lot of the current approaches don't really take this into account and end up looking in the wrong places for some of this activity. And the third dimension is behavior. We need to look for the behaviors that are intrinsic to the malicious employment of these TTPs. We need to get the right level of detail about those activities, and we need the contextual information around them to help us differentiate between malicious activity and benign activity. At the end of step 3, we will have defined and described a malicious behavior. We will have developed a hypothesis around it and how we would detect it, and we've thought through what kind of data are we going to need to test that hypothesis or feed that analytic. And we can repeat those 3 steps for each of the TTPs that we know adversaries use. Once we've done that, we need to filter that down to what we actually need for the hunt at hand. In a practical hunt, there are going to be certain technologies in use. There might be certain adversaries of interest that we want to prioritize. There might be certain time windows that are more important for us to look for malicious activity. And there might be certain behaviors that are more important for us to detect. And so we're going to want to filter down so that we can prioritize our efforts going forward. So, for example, if you're going to hunt in a Windows-only enterprise, you don't need to bring the malicious behaviors and associated hypotheses and data collection requirements associated with attack for ICS. If you don't have industrial control systems, you're not going to need that information. And this step is just a simple filtering down of the universe of information that's out there that the community has developed to what's relevant for your situation. At the end of step 4, we've developed our hypotheses and data collection requirements. We've filtered those down to what we need for our particular network, and we can pivot into the implementation phases of the methodology. So in step 5, we're going to figure out what data is already being collected, compare that with our data collection requirements, and identify any remaining gaps. We're then going to try to address those gaps. And there are different things that we can do. We can try to improve our instrumentation and sensing posture so that we collect more of the data that we need. We can fall back to backup analytic approaches based on the data that we do have available to us. And at a minimum, we're going to be able to communicate to the network owner about the amount of coverage that we have on the techniques that adversaries use for this network and where our gaps are. What this data collection plan will tell us is what's possible to see and what might be invisible to us, regardless of how effective our analytic approach is. Once we've done our best to maximize and optimize our data collection strategy based on our data collection requirements, we can start to implement our analytics in a real seam in the network using the actual data that we've started collecting. And we're going to want to test and validate and refine those analytics in our network. So some of these hypotheses were generated in the abstract. They might have been generated by someone outside of your team who had no knowledge of your particular network. And in this step, we're going to need to refine those based on the particular situation you find yourself in. Someone might have written an analytic based on the idea that malicious actors will use encoded PowerShell and assumed that benign activity will not use encoded PowerShell. But in your environment, you might have admins that typically use encoded PowerShell, and you're going to need to customize that analytic for your environment to avoid the false alarms that are going to arise. And we're also going to want to red team or emulate threats in our own network to validate that these analytics will detect that activity. This is the stage when we're really going to put precision and recall to the test. As the threat emulation team emulates the individual behaviors that we believe we can see with these analytics, we're going to check to verify that those analytics do fire each time that the threat emulation team implements them in our network. And we're also going to look at false alarm rates. And we're going to tweak the analytics and purple team with our threat emulators until we have a good balance of precision and recall for our network. Now, at the end of step 6, we have a very solid foundation on which to begin our hunt. We have taken a very thorough approach to understanding the behavioral invariants that are known to be used by malicious actors. We have developed an analytic and data collection strategy based on that knowledge. We have customized that strategy for our environment, and we have validated that our implementation will have good precision and recall in our environment for those behaviors. That sets us up for a much higher probability of success in our actual hunt. And so now we move to the final step of the methodology, step 7, which is to actually conduct the hunt. And there are two different components of hunting. There's a detection component where we get our first hit. The first thing that is going to justify some investigative work to triage what we've seen and determine whether it's benign, suspicious, or malicious. And then we're also going to want to pull the thread on some of those hits. We're going to want to gather contextual information that will help us discriminate benign from malicious, so that we can move the events that were categorized as suspicious into one of those other two bins. And we're going to expand out our knowledge of the malicious activity that we've seen so that we get a more comprehensive view of the end-to-end campaign that our adversaries were conducting in our network. That's going to give us a better position from which we can take action. Now, taking action is outside of the scope of this training, but it will range. There's lots of different options for kinds of actions we could take. Quarantining and blocking is just one possibility. We could also conduct deception operations or do other things, but we want to have a pretty solid understanding of the full scope of the adversary activity thus far before we take an action, so that we can be strategically smart about which action we choose, so that we can have maximal impact on the adversary and not only stop the first thing that we detect, but effectively stop their entire campaign. So those are the 7 steps of the methodology. Again, this sounded pretty sequential, but in practice, it will be very iterative. There'll be micro iterations within steps. There'll be iterations between steps, and you'll be iterating through this entire V. As you learn more about techniques, as you learn more about your network, as you detect real malicious activity in your network, you will want to go back and update, and you'll want to keep this an ongoing process so that you're continually improving and refining your approach. So, in summary, this training is going to dive deeper into this entire 7-step hunting methodology. This methodology is different from some of the legacy approaches, such as signature-based or anomaly-based detection, but it's complementary to them. They can be used in partnership with each other to provide more holistic coverage and understanding of your network and any malicious activity that's going on. This training is going to help prepare you to detect malicious activity through an understanding of adversary TTPs described at the behavioral level.